Next we are discussing refraction at a spherical surface. See, these are water drops and the surface, the shape of water drop is nearly spherical. You can see image of flowers in the drop. This is due to refraction of light. Light from that flower is coming through this to your eye. That's how you see this flower inside the drop. So this is due to refraction and the surface is spherical. But we aren't taking a water drop, we will be generally taking a little more exactly spherical surfaces. Like this is a paperweight like thing, globe of a glass, hemisphere. It has got a spherical surface almost, a refracting surface. Refracting means it should be transparent. A transparent surface which forms part of a sphere. This you can see is a part of a sphere, is what we call as a refracting spherical surface. Okay. Now, when you deal with such surfaces, which actually leads you to lenses later, we need to use Cartesian sign convention again. We studied that for a mirror. Now, we are going to study that for such spherical surfaces. Concepts are almost the same. Okay. What is positive direction? That is the direction of incident light. That's a basic idea. Right. Now, according to Cartesian sign convention for a spherical surface, all distances must be measured from the pole. I will explain this. This is a spherical surface, but in my diagram I will represent it like this. That means there is a spherical surface, there is one medium here and there is another medium which is continuous. Okay. Now, from where will you make all measurements? For the spherical surfaces, this point here, that is from where you measure it, everything. Suppose you have an object here, somewhere here, an object here, then light from the object will fall to the surface in this direction and this direction will be taken positive. Direction of the incident light must be taken positive. Now, suppose you want to know what is the distance to the source here, then your measurement should start from here in the opposite direction. So that will become negative. Suppose an image is formed here. Suppose an image is formed there, here. Then you need to measure it from this point, like this. So that will become positive because it is in the direction of the light. All measurements must be from the surface here. You can call it as a pole. If you measure anything like a height upward, that should be taken positive, downward taken should be negative. Same concept. In the case of a mirror, you were following the same thing. So, all distances are measured from the pole of the spherical surface. I explained. Distances measured in the direction of light positive, opposite negative. Distance upward positive, downward negative. But we also do certain assumptions here. What is that assumption? The object is a point object lying on the principal axis. I will tell you what it is. This is the surface. Suppose this is the pole, you consider the principal axis like this, an axis passing like this. And you also know that this spherical surface, this is part of a sphere that will have a center. It is called center of curvature. This is called pole. This is called principal axis for the spherical surface. Objects must be on the principal axis and object must be point object. That's for easiness. You consider point object. You can consider tall objects, no problem in that, but in this basic level it's better to start with a point object. And again, how much area of the surface are you considering? For example, I can consider this much area. I mean, this whole area can be calculated, this whole surface. That means there is a large area where light can actually incident. Light, this much is exposed area. Or I can take only a small section of this. I can take a small section like this, only this much area. Then this is called small aperture, the other one is called large aperture. This is small aperture. But if you take the other one, that has got a large aperture. You always take only a small aperture. What is the meaning of this thing? I'll explain it. In this spherical surface, you are not taking the whole surface area, you are taking only a small portion of this. You are taking a small portion, only this much. The aperture will be very less. Okay. So, the object is a point object lying on the principal axis. The aperture of the refracting surface is small. You are taking only a small section of that one. The incident ray and the refracted ray makes small angles with the principal axis. Okay. In mirror or lenses, if this is principal axis and light rays are coming parallel or making small angles, which will fall near the pole, mirror or lens anywhere, this is the pole. If the light rays are making small angle like this or coming very close to the pole, these are called paraxial rays. Paraxial rays. What are paraxial rays? Light rays incident very near to the pole, making small angle with the principal axis are called paraxial rays. So, you are considering only paraxial rays. But in our diagrams, they may not appear so, but this is a concept. Because making small angle diagrams will become complicated to see. So, we may take a large angle where assumption is always about a small angle. So, this is what we are going to do. I am coming back again. We are doing refraction at a spherical surface like a water drop or a glass surface, which will be considered like this. And for this we follow certain assumptions, Cartesian sign conventions. Then small object, point object, small aperture. Okay. Now, if I have surfaces, there are various options for surfaces. You can, this is convex. This side can be rarer. This can be denser. This can be rarer and denser. See, this can be rarer, this can be denser. That is one option. Second option, this can be denser, this can be rarer. That is another option. We can go for any of this. Now, this is a convex surface. Convex surface. You can consider concave surface also, or even otherwise, when you look from this side, this is a concave side. When you look from this side, it's a convex side. Like I have a principal axis here. If I place an object here, object is facing the convex side. And if I place an object here, object is facing a concave side. Any of this can come. But whatever it is, with a single derivation, we can control everything. Single derivation for any such cases. What are the different cases? Convex rarer, convex denser, or concave denser, concave rarer. Any of these four combination we can do with a single derivation. Okay, that is what we are going to do next. The same surface, I am going to convert that into a simple diagram. So, I have a convex surface, and that surface is represented by this line. And there is a medium N1, there is a medium N2. This is medium N1, this is medium N2. And N2 is assumed to be a continuous one. N1 is again assumed to be continuous one. This is the interface which is spherical in shape. Object is O, point object, as we said earlier. And these angles alpha, beta, gamma, all are small angles. In NCERT textbook, you may not see alpha, beta and gamma. They just write it as angle NOM. But for my convenience and for your convenience, I am taking alpha, beta and gamma. Okay. I told you about a small aperture. What is the advantage of small aperture? If aperture is small, then when you draw a normal like this one, this distance will become negligible. We did this in the case of mirror also. Same assumption. Okay. So, let us start. refraction at a spherical surface. Refraction at a spherical surface. Consider a spherical surface separating two media of refractive index N1 and N2. For easiness, I am taking N1 less than N2. So what does it mean? Light is going from rarer medium to denser medium. Okay. There is a point object here. O is a point object. This is the principal axis. This is the center. This is the center of the spherical surface. C is the center of the spherical surface. So naturally, this distance is the radius of curvature. So I presented different points, N1, N2 refractive indices, N1 less than N2. Light is going from rarer to denser. Object is O, radius of curvature is R, center of curvature is C. Pole, I use the letter M, and there is a point N where light is incident. Okay. Now, consider one light ray from O going like this. What will happen? This is going along the radius. You can see this is the radius, so this is normal incidence. Spend 2-3 minutes to understand how it is normal incidence. This is normal incidence and this will go straight. That light will not go it will not undergo any deviation, it will go straight. But another light ray which will go like this up to this point here. I need normal at that point, and I know normal is the radius. So from the center, if I draw a line like this, this becomes the normal at that point. So incident light normal, I can immediately mark this as angle I. I got angle I normal. Where is angle of refraction? And I told you earlier that N1 is rarer, this is denser. So instead of going straight like this, the light will not go straight, this will bend towards the normal. So this is the refracted light ray, and that light ray is making an angle R with respect to the normal. So you got angle I and angle R, and this light ray after bending from here will go and meet the straight light ray here. So this is the point where you get the image. So O is a point object and I is the point image. So your diagram is okay. Now drop a perpendicular from N to the principal axis. This is a perpendicular, but I say this gives you a triangle, but these 2 points are very close. So always I use this point equal to M, because that is negligible. What do you want? You want a relation between U, which is the distance from the pole to the object U. Then you have V, which is the distance from the pole to the image distance. And you have R, the radius of curvature of the spherical surface. Then you have N1 and then you have N2. So you need to get a relation between all these 5 quantities. It's not going to be easy. Okay. And what is the final equation that we are going to derive? The final equation that we are going to derive is like this. It is N2 by V minus N1 by U equal to N2 minus N1 divided by R. This is the equation that we are going to derive. So it starts. So you have the diagram, various parameters, you have the final equation, and what am I going to do for this? Let us start. Apply Snell's rule at point N here. At this point I am going to apply Snell's rule. And how to apply Snell's rule? Snell's rule at that point will be written like a N1, which is N1. N1 is the surrounding medium N1, and in that medium you have this angle I, N1 sin I, N1 sin I equal to, this medium has got a refractive index N2, so I will write like a N2 sin R. But I said these are paraxial rays, all angles are to be considered very small. So, and see in my diagram there is a large aperture, but practically aperture must be as small as possible. Therefore, all angles will be very small. So, we can write N1I equal to N2R, small angle approximation, sin theta equal to theta, theta measured in radian. Now, I have considered an angle alpha here, this angle alpha at the object, angle beta at the image, and angle gamma at the C. For this triangle NOC, see the triangle NOC, this is a normal. In this triangle NOC, I is the exterior angle. So, I should be equal to alpha plus gamma. So, I is equal to alpha plus gamma. Do not confuse with the R and gamma, that is why I write R like this and gamma like this. Okay, when you write, be careful. This should be equal to N2 into, in the triangle NCI here, NCI, gamma is the exterior angle. So, R plus beta should be gamma. When you listen, write this in your book so that you can understand gamma is R plus beta, but I want R. So, what is R? R is nothing but gamma minus beta. R plus beta is gamma, so R is gamma minus beta. Fine. Now, N1 times, we are doing small angle approximation, therefore, sin theta equal to theta equal to tan theta. So, alpha is nothing but tan alpha. Alpha is equal to tan alpha. Alpha is equal to tan alpha, and I can say tan alpha, watch out, I am writing tan alpha as Mn divided by C. This is alpha. The triangle is actually this perpendicular, but I can say it is almost equal to Mn. M. This is M, this is N. This point is very close to M, that is why I say Mn. Mn is the vertical side, Mn divided by Mo, that is alpha, Mo. Plus, same manner, what is gamma? Gamma is this angle, that is Mn by Mc. Mn by Mc, okay, equal to N2 times. Gamma we wrote just now, it is Mn divided by Mc minus, what is beta? Beta is nothing but Mn by Mi. Mn is common everywhere, Mn by Mi. Now what? Mn comes common everywhere, so it get cancelled. So this will give you N1 by Mo, I open the bracket, plus N1 by Mc equal to N2 by Mc minus N2 by Mi. You fed up with this? No chance. Many things are coming, much more is waiting for you. Okay. Now, there are two MC terms here, so it is better to club them into one side. So, I will rearrange them, N1 by Mo, let it be here. I will take this to this side, plus N2 by Mi equal to, this is N2 by Mc minus N1 by Mc. So, we got to this much of steps. Now what is MO? Okay, now Cartesian sign convention. I know many of you are finding it difficult to handle Cartesian sign convention. This is one more chance to learn that one. Where is the object? Where is the surface? This is the object, this is the surface. So, light should fall on the surface from the object. So, light is coming from O to M. So, this direction should be taken positive. All measurements must be from the pole M. So, if you want to measure object distance u, MO, what is MO? What is MO? MO is what? MO, is it equal to u? No, no, it is not equal to u. But people will say, why? It's u. Sir, it is u. But you have to use Cartesian sign convention. So, u is correct, but with the sign, its opposite light, it must be minus. Okay. What is M? So, MO I handle. What is MI? What is MI? M is here, I is there. So, I have to measure it from M to I in the direction of the, it's positive, and that is what we call as the image distance V. What is MC? What is MC? MC is nothing but, C is the center of curvature, it is the radius of curvature, that is plus. So, this is plus, only U is minus. We have to substitute that here. Okay. When we substitute that here, I am substituting that here. So, I will get N1 divided by, what is MO? Equal to minus U plus, what is it? N2 divided by, what is MI? MI is plus V equal to, this I can combine because denominator is same. So, this can be written as N2 minus N1 divided by, what is MC? MC is nothing but R. A slight rearrangement because we prefer positive term to start the equation, N2 by V minus N1 by U equal to N2 minus N1 by R. Arey wow, this is what we have been waiting. We got it. Now, another important instruction. What is it? Whenever you do this question, you have to apply Cartesian sign convention again. In every problem, you can't directly use this. You have to put the proper sign of U, V and R. Okay. So, what is this equation for? This is the relation between image distance, object distance for a spherical surface. And this is applicable for convex surface, concave surface, rarer to denser, denser to rarer, any kind of surface. If it is spherical single surface, apply this. My guarantee. You will not go wrong if your Cartesian sign convention is correct. We will try this out in a question. Okay. So, this is a whole derivation. I have actually skipped the statements that you have to fill in because I used the idea sin I equal to I. I did not write that on the board, but when you write down the note, you listen to every sentence that I am telling and write down the proper steps, because without steps you won't get mark in the board examination. For entrance you need only this. Okay. We will do a question right now. So, just now we studied about refraction at a spherical surface, and this is an example given in the NCERT textbook. You can see that light from a point source, I told you point source, in air, so source is in air, falls on a spherical glass surface where the refractive index 1.5 and the radius of curvature is 20 centimeter. The distance of the light source from the glass surface is 100 centimeter. So, glass surface and the light source are at 100 centimeter. At what position the image is formed? You need to find out image position. Okay. So, let us proceed. So, we got the idea. So, I can just say this could be that spherical surface. There is a spherical surface and there is an object. Say this I can consider as air. So, this becomes glass. This is the principal axis, and I said all our questions we will keep the object on the principal axis, and there is a point source. And where is the point source? It is given as in air. And one more point, this spherical surface has got a radius. Its radius is given as 20 centimeter. Okay. So, I can say this is a spherical surface. So, this is the center of curvature. this is given as 20 centimeter radius, and the object is at 100 centimeters. So relatively this is 20, so 5 times larger. So somewhere here is your object. So naturally light ray will go straight one like this, and another one falling up here may bend like this and forms images here. This is what I expect. Let us check whether it is correct. Let us do that using the equation. And what is the equation for this one that we derived earlier? N2 by V minus N1 by U equal to N2 minus N1 divided by R, with this Cartesian sign convention. And what is U, what is V, what is R? R is given. What is R given as? R is given as R equal to 20 centimeter in the question, and object is kept at 100 centimeter given in the question. V I have to find out, not given. What is N1? N1, air, refractive index is 1. I told you in the video it's 1.00029, but take it as 1. And what is N2? N2 is the second medium, refractive index is given as 1.5 in the question. So all the data is available. Okay, so let us calculate. Cartesian convention, Cartesian sign convention, which should be positive direction. Object is here, light is going in this direction, so that must be the positive direction. This is positive. Where is object? Object is here, U. U should be measured from the pole against the light in this direction, so U must be minus 100. R is measured in this direction, so R is plus. V I don't know, so I don't have to give any sign. N1 and N2 just use their numbers. Now substitute. What is N2? N2 is 1.5 divided by V, I have to find, minus N1, 1 divided by U minus 100 equal to N2 1.5 minus 1 divided by R equal to 20. Okay. I want V, so I will keep this as 1.5 V here equals, I will take this is minus and minus plus, but that will go there, it will become minus 1.5 minus 1 is 0.5, so that is 0.5 divided by 20, then minus, see, minus and minus become plus, but when I take to the other side it will become minus again by 1 by 100. So simplify. You can follow your own method, I will follow my own method, but the final answer must be the same. 1.5 I think I will better write it as 3 by 2V, because that makes easy calculation, because decimal points sometimes may give you wrong answers. 0.5 is 1 by 2, so this will give you 1 by 2, 1 by 20, 1 by 40 minus 1 by 100. Okay, this I can work out as 3 by 2V equals, I'll take the common denominator here. So this will give you 100 minus 40 divided by 40 into 100. Okay. I need more space. This gives me 3 by 2V equals 60, 100 minus 40 by 40 into 100. Now this 0 cancels this 0. This 3 will cancel this 6 to 2. Okay. This 2 will cancel this 4 to 2, and this 2 will cancel this 2. So by the end I will get 1 by V on left side and 1 by 100 on the other side. So taking reciprocal, I will get V equal to 100. It is not minus 100, it is 100. So this is a positive 100. What is the meaning of the positive 100 here? V should be measured from the pole. Okay, it should be measured from the pole, and in which direction? In the positive direction. Positive direction is what? Right side direction. So, from the pole to the right. So, here this is where I am getting the image at 100 centimeter from the pole, that is inside the glass. Clear? For an observer here, this is how he appears, provided the glass has got a continuous structure there. So, this is the answer. So, I applied the equation and I used the Cartesian sign convention. Dear children, you don't simply listen to a problem, you have to do this. After watching the video, do this by yourself. You will get lot of confusion even in a simple problem. Only when you do that by yourself, you will master it. Okay, practice this.